In this video, we are going to prove that for all natural numbers n, 2 to the power n plus 3 to the power n is never a perfect cube. Before we move on, don't forget to give a like, subscribe to my channel, and turn on post notifications. Here are some examples when n takes small positive integer values. When n equals 1 to 4, the given expression is indeed not a perfect cube. But this is clearly not enough to prove that this is always the case for all natural numbers n. So I'm going to give a proof next to the examples. To prove that for all natural numbers n, the given expression is never a perfect cube, we usually need some tools on modular arithmetic. For example, I can pick a positive integer, say p. Then I'm going to consider the remainder when 2 to the power n plus 3 to the power n is divided by p. Then according to the general rule of what remainders can a perfect cube have after dividing by p, we have to prove that for all, or at least for most cases, 2 to the power n plus 3 to the power n do not have those remainders after dividing by p. And this number I'm going to pick is 9. Notice that for n at least 2, 3 to the power n is congruent to 0 mod 9. This is because starting from n equals 2, 3 to the power n is a multiple of 9. And after keep multiplying by 3, the remainder is still the same. It's still 0. While for 2 to the power n, starting from 4, and the next we'll have 8 mod 9, and then, which is actually minus 1. So the next one will have to be minus 2, or I can replace the 8 by minus 1, and then we have minus 2, minus 4, and 1, and so on. In fact, after the number 2, this period repeats itself, and we know that these are all the possible values that can possibly be taken when 2 to the power n is divided by 9. Now, generally speaking, under mod 9, a cubic number can only be 0 or plus or minus 1 mod 9. To show this, I'm going to write n equals 3 times big N plus r, with r being the remainder when n is divided by 3. So big N and r are both positive integers. Or for only n, or I should say it's just not negative. I should not say it's positive. Sorry for the error. Now for this, notice that n cubed is 3 times big N plus r all cubed, and by expanding we have 27 big N cubed plus 27 big N squared times r plus 9n times r squared plus r cubed. And so if we want to find the remainder when n cubed is divided by 9, it's just the same as looking at that when r cubed is divided by 9. But r is just bounded by 0 and 2. So we have only 3 possible values, which are 0, 1, and 8. But 8 is congruent to minus 1 mod 9, so I can replace that by a number that is much closer to 0. Now looking at this, you may notice that the only possible value, or I should say the possible remainder, that 2 to the power n can take is -1 and 1 under mod 9. And this can only hold when n is a multiple of 3. Or I should let n equals 3k, k being a positive integer. Now we can go back to our given expression. So we have 2 to the power 3k plus 3 to the power 3k. Notice that for this expression, it is always larger than 3 to the power 3k. But on the other hand, comparing this expression with 3 to the power k plus 1 all cubed, this is clearly smaller because for this cube, we can expand it and c is equal to 3 to the power 3k plus 3 times 3 to the power 2k plus 3 times 3 to the power k plus 1. And even the second term itself is equal to 3 times 9 to the power k, and that is larger than 8 to the power k. And so we know that our given expression must be smaller than 3 to the power k plus 1 all cubed. And since 3 to the power 3k can be written as 3 to the power k all cubed, that means our given expression is between two consecutive perfect cubes. So from this we know that can never be a perfect cube. To wrap up our proof, there's actually one more minor detail that we should take care of, is that the result that 3 to the power n is congruent to 0 mod 9 is based on the assumption that n is greater than or equal to 2. So we need to add just an extra line at the end to say that to take care of the case when n equals 1. Of course, again, it's not a perfect cube. So then our proof, the things written in red, will be complete. And so that means for all natural numbers n, 2 to the power n plus 3n is not a perfect cube. And so this is the end of the proof. Please feel free to share your ideas in the comments. Thank you for watching. See you next time.